Hi everyone, in this video we are going to discuss electromagnetic radiation. And the reason we are going to start talking about radiation or electromagnetic radiation is because we are trying to determine why the ozone layer is so important. So we know the ozone layer, or ozone specifically, can absorb electromagnetic radiation, or it screens the earth from electromagnetic radiation, but we don't really know what that is or how it does it. And so we're going to start off by just doing a global explanation of what electromagnetic radiation is. And the first thing I want to point out is that sometimes people abbreviate electromagnetic as just EM. So if you ever see EM, we're just saying electromagnetic. Okay, so what is electromagnetic radiation? So EM radiation is simply a continuum of waves, and this is actually the really important part, of varying energies, okay? So all of these different types of waves have several different types of energies, and they vary all the way from something really tiny, so a small amount of energy being transferred, or you can have a vast amount of energy being transferred. And we'll dive into this a little bit deeper later on in the semester, but the ones of really high energy are actually really bad for us. So let's go through and actually talk about this continuum of waves. And so the continuum of waves is sometimes referred to as the electromagnetic spectrum. So let's dive through the spectrum. So on the far most left side, we start with gamma rays. So gamma rays, so G-A-M-M-A, gamma rays are very high energy. Okay, so when I say high energy, from here on out, when we're talking about waves, you need to be thinking danger, danger. And so just to put this into context, gamma rays are usually discussed in terms of nuclear chemistry. So we'll come back to this and talk about it in depth in a few units from here. All right, so after gamma rays, what we have are X-rays. Okay, so X-rays are the next highest in energy. Typically, we use X-rays when we're talking about anything medical. So I've hurt my knees several times, and I've had countless X-rays on them. It is something that's used to diagnose injuries, but here's the thing, X-rays are higher in energy. You don't really want to have that many, so if you can ever limit your exposure to X-rays, I would definitely encourage you to do that. Now the next three we're going to do in a group. So we have UV, we have Vis, and we have IR. So let's break those apart. So ultraviolet, violet, visible, and IR, or infrared. Now the reason I did the three of these together is because all of these are what come directly from the sun. Now the IR, we have about 53% of that, of the sun's energy comes in terms of IR. IR is where you feel heat. So if you've ever stood in front of a fireplace and you actually could feel the heat or the thermal energy coming from the fire, that's IR energy. Visible is what you see, okay? And so in terms of the sun's energy, about 39% of it is transferred into visible light. So our retinas are actually tuned to be able to look and pick out the different colors of our visible spectrum. So we're going to come back to this one because I think it's really actually kind of cool to see that. And then ultraviolet, we're going to come back to that for sure. And about 8% of the sun's energy is actually transferred in terms of ultraviolet light. So this is the one that is really important when it comes to ozone. So we're definitely going to come back to this section. Now the last two we're going to talk about are our ones that are lowest in energy. So we have micro, also known as microwave. Okay, we've probably heard of these before. And then we also have radio. And radio doesn't really have a letter, so we just write radio. Radio is our lowest in energy. So in your mind, you should be thinking these are the safest. And just to give you kind of an idea of the difference of these, the radio wave has about 10 to the 2 meters in terms of a wavelength, where a gamma ray is actually 10 to the negative 14 meters. So it's really tiny. So when something has a really tiny wavelength, it's actually really high in energy. And the opposite for it, when something has a really large wavelength or a really long wavelength, it's actually really low in energy. So we'll come back to that later, and you'll see all the calculations and all the fun part of it. But just right now, we just want to get you a grasp on what the electromagnetic spectrum actually is. But before we move on, I want to move a little bit more and talk about the visible region, and I fully expect you to understand all of this, know everything I'm about to write here. So the visible region goes from 400 nanometers to about 700 nanometers. Now, the 400 nanometers is blue light, where 700 nanometers is your red light. And now it goes this way in terms of the rainbow, right? So you would have red, then orange, then yellow, then green, then blue, then indigo and violet, and so forth and so forth. So what I expect you to know is simply this, that at the one end you have a visible light, which is blue, which is 400 nanometers. This, out of the visible light, is going to be your highest in energy. On the opposite end of your visible region, you have something at 700 nanometers, which is your red light, and this is going to be your lowest in energy in terms of just visible energy when we're just looking at that. And so what I've introduced here is a unit that we need to become very, very comfortable with. Nanometers is the one we most commonly use because that's our visible region. It's the type of light we can actually see, and we can actually produce, and we can actually work with it. And so what we need to do is figure out what 1 nanometer means. And so one conversion that we like to use is that 1 nanometer is equal to 1 times 10 to the negative 9th meters. So knowing that, what I want you to do is take this number right here, 7 times 10 to the negative 7th meters, and I want you to convert that to nanometers. Go. Did we get an answer? Hopefully we did. We had to do a little bit of dimensional analysis here in order to convert, but let's just do it together just in case we got a little tripped up here. So the first thing you do is start with 7 times 10 to the negative 7 meters. We know that for every 1 times 10 to the negative 9 meters, we have 1 nanometer. And so our meters cancel out, we're left with nanometers, and when we multiply, or well, we actually take 7 times 10 to the negative 7 and divide it by 1 times 10 to the negative 9th, we end up with 700 nanometers. So what I could have done is said, what color of light is represented by something with a wavelength of 7 times 10 to the negative 7? And hopefully you would have seen that and been like, red, 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 it's definitely red. So hopefully that made sense. Take care of yourself, drink water.